This video is about solving polynomial and rational inequalities. Here are examples of some polynomial inequalities. In the first example, we have polynomials on both sides of the inequality. In the second example, we have a polynomial on the left-hand side that is compared to 0, and this polynomial is already in a factored form. Rational inequalities look like this. We may have a rational expression and compare it to 0, or we may have two rational expressions on both sides of the inequality. Obviously, such inequalities can be converted to the first case. How do we solve inequalities? Well, we can solve them graphically or algebraically. So, which way it is better to do it then? Actually, we need to know both methods. Graphical solutions are usually easier, but not always exact, as often we are unable to rate the exact roots directly from the graph. If we already have a graph, it's usually easy to tell when the graphed function is above the x-axis or below the x-axis. That means it's easy to solve inequalities that compare the left-hand side to 0, like this one or that one. However, we also need to know how to solve polynomial or rational inequalities algebraically, just by inspecting the inequality without a graph. Let's see. In the first example, we want to solve the inequality x squared minus x bigger or equal to 12 using the graph of the related function. How does this function relate to our inequality? Notice that it's enough to move the 12 to the left-hand side, and then we create a function x squared minus x minus 12. Since we want this function to be bigger or equal to 0, we're really looking for those x's that will make the function above the x-axis, above 0. So here's the graph of our function. As we see, the graph is above 0 for x values below -3 or above 4. Exactly at -3 or exactly at 4, the function assumes value 0. So those 2 points will also belong to the solution of the inequality. Therefore, we can record that based on the graph of our function, f of x is bigger equals 0 for x's from -infinity until -3, including -3, or, meaning union for the two intervals, from 4 to infinity. Okay, those are the two intervals that we are taking as the solution. So, since we know that f of x is bigger equals 0 for x's from the set of points, therefore x squared minus x minus 12, which is our function, right, is bigger equals 0, and equivalently x squared minus x is bigger equal 12, our original inequality, for the same set of x values. So that's the answer for the whole question, right? Notice that if we would need to solve the opposite inequality, for example, when x squared minus x is smaller than 12, again, we could read the answer from the graph as the interval from -3 till 4. So that's the region on the x-axis satisfying the inequality x squared minus x smaller than 12. So the answer to this inequality would be from -3 without -3 till 4, right? But this is another question. Okay, so we can erase this. As we see, there's no trouble to get the graphical solutions. However, we really need to learn how to solve inequalities algebraically. Let's use an algebraic method in the second example. Solve the polynomial inequality like this by analyzing signs of all factors. Notice that our inequality has 0 on one side, and the left-hand side is already in factored form. We have exactly 3 factors. How this may help us? Well, we are interested only in signs that this polynomial assumes in different sections of the domain. We don't really need to fully evaluate this polynomial for particular x's. The only thing that we really need is to analyze the behavior of signs assumed by this polynomial. As soon as we know that for a particular x, the polynomial becomes negative, we know that this x belongs to the solution set. So the idea is to list all the factors in a table like this. Each factor will get its own row, then underline everything. This line will serve us as a number line, and then we are going to record the result of the product of these three factors. So this will be our table of signs. Now, on this number line, we are going to mark the important points. We'll refer to them as critical points. Those are the x values that make each factor equal to 0. So the first factor equals 0 when x is 0. So we mark 0 on the number line. The second factor becomes 0 when x is equal to 2. So we mark 2 on the number line. And the third factor becomes 0 when x is equal to -1. We make sure to mark those points in increasing order. Just follow the regular order on the number line, right? Each of those critical points will cut the whole domain of all real numbers into sections. So we have a section from -infinity until -1, from -1 till 0, from 0 to 2, and from 2 to the infinity. Now we are going to investigate how those factors behave in each section of the domain. We are only interested in signs that a particular factor assumes in each section of the domain. So we know that x changes its sign at 0. If x's are larger than 0, then this factor is positive. We record a plus here. So above 0, the x is positive, and below 0, the x is negative, right? Now the second factor, x minus 2, becomes positive when x's are larger than 2. Therefore, 2 is our critical number. This expression becomes 0 when x is 2. However, if x is larger than 2, this expression is positive. So we record a plus here. If x's are below 2, the whole factor x minus 2 is negative, all the time negative to the left of this critical number, right? Similarly with x plus 1. X plus 1 is positive when x is larger than -1. So any region above -1 will get the positive sign, and below -1 becomes negative. The critical number for this expression is -1, which means that the expression changes its sign at this moment. First it's negative, then it's 0, and then it's positive all the way to infinity. Okay, as soon as we have this table of signs, it's easy to decide about the resulting sign of the product of those factors. If we multiply 3 negatives, the answer is negative. If we multiply 2 negatives, the answer is positive. 1 negative gives us negative, and there's no negatives, therefore the answer is positive, right? So here's the visual sign distribution that we can use to answer the question, when this whole product, when the result is negative. Well, let's mark it. It's here for sure, and it's over there. So from -infinity until -1, should we take -1 or not? Well, we don't have the equal sign here. If x is -1, the whole expression will be exactly 0. So it won't satisfy this strong inequality, right? Therefore, we have to exclude the -1. Next, we need to make decision about 0. Should we take 0 or not? Again, no, because there's no equation here. So the left-hand side can't be equal to 0. We have to exclude this point. And similarly, 2 has to be excluded for the same reason. Okay, so now we are ready to give the final answer. We see our solution. Those are the two intervals. We need to connect them by the union sign, right? Therefore, our inequality is satisfied by all x's from -infinity until -1, round bracket, no endpoint, union, and then from 0 to 2. Okay, here it is. We didn't have to graph this polynomial, and we could still solve the inequality analyzing the signs of all factors. So that's the algebraic method of solving inequalities. Let's try the next example, a rational inequality. First, let's observe that the left-hand side of this inequality is always positive or zero, never negative, just because we are squaring or raising to the fourth power. So we can notice that the left-hand side is always bigger equals 0 in its domain. That means we consider only the x values for which the expression can be evaluated. Since 0 is always bigger than -1, therefore this left-hand side is always bigger than -1, meaning this inequality is always true, but for all real numbers in its domain. We need to remember the domain part. What is the domain of the left-hand side? Well, those are all real numbers except for 0. We can't plug in 0 for this x because the denominator would be 0 and that's not allowed, right? So, the solution is all real numbers. Every x value is fine except for the one that will make the denominator 0, so we have to exclude 0. That's our final answer. All real numbers but not 0. So that was kind of exceptional example. Just by analyzing both sides of the inequality, we could tell that it is always true. Notice that if our inequality would be reversed, for example like this, then we would have no solution at all. You may want to pause the video and justify this result to yourself. On the other hand, most cases, most rational inequalities will actually need to be analyzed more thoroughly. It's not only no solutions or all real numbers. Let's solve the next inequality, observe the steps we're taking to solve it, and record them to develop a general strategy. The first step would be to make sure that we compare a rational expression to 0. This is actually a critical point. We must have one side of the inequality equal to 0. Otherwise, we won't be able to use the sign analysis, isn't it? So we can't have 3 on this side. We need to bring it to the left. Okay, so the first step is keep one side equal to 0. Let's see how it works. After bringing the 3 to the left, we have x minus 1 over x plus 2 minus 3 smaller equals 0. Great! Now, since we are going to analyze the sign of the left-hand side expression, it's convenient to keep it in a single fraction form, with the numerator and denominator factored completely. So the next step will be keep the other side in the form of a single fraction. That means we need to recall how to work with rational expressions, how to add or subtract rational expressions. We need the common denominator, which in this case is x minus 2, right? Let's copy the numerator as it was in the first fraction, and then it's minus. The 3 gained a new denominator, therefore we need to multiply 3 by this denominator x minus 2. Okay, everything is smaller equals 0. Now let's clean up the numerator. We'll release the bracket and collect like terms. So we have x minus 1 minus 3x and plus 6 over x minus 2 smaller equals 0, which is equivalent to negative 2x plus 5. Negative 2x plus 5 over x minus 2 smaller equals 0. So, at this stage, we already have a single fraction. In case we end up with some higher degree polynomials, either in the numerator or the denominator, we need to factor completely both the numerator and the denominator. In our example, everything is already in a factored form, so there's nothing else to do here. In the next step, we'll analyze the signs of all factors, like in example 2, and record them in a sign table on a number line. So let's prepare a sign table. We're going to analyze these two factors, negative 2x plus 5 and x minus 2. Let's make the 2 rows, and here will be the result. What are our critical numbers when negative x plus 5 is equal to 0? Well, we can calculate this on the side. Negative 2x plus 5 is equal to 0 when 2x is equal to 5, therefore when x is equal to 5 halves, 2.5. So let's say 2.5 is somewhere there, okay, 5 halves. And the next critical number comes from this expression. X minus 2 is equal to 0 when x is equal to 2. 2 is below 2.5, so let's mark it somewhere here. That will be our 2. These two critical numbers cut our number line into 3 sections. So now we are going to analyze signs in those 3 sections. The top expression changes its sign at 2.5. When is it positive? Above 2.5 or below 2.5? Let's say if I choose a testing point, for example 0, which is definitely below 2.5, let's see the sign. If x is 0, the result of this expression is 5. This expression is really positive. Therefore, below our critical number, the expression assumes positive signs, all the way positive until this critical number 5/2, when the expression becomes 0, and then if the x's are higher than 5/2, the expression is negative all the way till infinity. The second factor changes its sign at 2. If x's are higher than 2, for example 3 or 5 or anything higher, we see that the value of the expression is positive. And below 2, for example, if x is 1 or 0, the expression is negative. Okay, so to the left of 2 is negative, to the right of 2 is positive. Now, when we already have our signs, let's talk about the result. When we multiply or divide, in this case divide, two different signs, the result is negative. If we play with two positive, the result is positive. And again, two different signs, the result is negative. So we are going to read the solution set from the table of signs. How to read this? Let's go back to the inequality to check again what is it that we look for. Well, the left-hand side, this quotient, needs to be smaller or equal than 0. So we're choosing the x values that will make the overall quotient negative or 0. We see the negative section here and over there. We also need to watch the endpoints. Always check the endpoints. Decide which one to include in the solution set. Make sure to exclude any values that are not in the domain of the original inequality. So watch for the domain. Okay, so what's the domain of this expression? Well, that's all real numbers, but we can't make the denominator 0. The x that makes it 0 is 2. Therefore, we need to exclude 2. Since 2 doesn't belong to the domain, it can't be included in our final solution. So we put an open circle here. Everything from minus infinity until 2, but without 2. What about 5/2? Well, 5/2 is in the domain. Also, 5/2 will make the left-hand side expression equal to 0. Since we have equation included in our inequality, we are okay to have left-hand side equal to 0. 0 is allowed because equation is included. Therefore, we take this point as one of the solutions. We include it to the solution set. Okay, so we are ready to give the final answer. The solution to our original inequality is the set of all x's from minus infinity until 2 without 2, together with the interval from 5/2 with 5/2 until infinity. So that's the final answer. The inequality was solved algebraically. Now, if you have time and energy, you can always plug in this expression, the left-hand side, to the calculator and confirm the answer. However, it is important that we learn how to solve such inequalities algebraically, using the sign analysis. Let's practice. Solve each inequality and graph the solution set. Give the answer in interval notation. Remember that unless it's written solve graphically, we are expected to solve algebraically. Okay, let's follow our steps. What should we do first? We already have 0 on one side of the inequality, that's great. Now we should factor this quadratic trinomial. Since the product is 6 and the sum is 6, we can't really factor it in integers. Therefore, it will be useful to find the roots of this parabola. We can do it by using the quadratic formula. x, 1 or 2 is equal negative b, which is 6, plus or minus b squared, which is 36, minus 4 times a times c. Okay, everything over 2 times a, which is 6. Okay, so we have 6 plus minus root of 36 minus 24. That gives us 12, root of 12, everything over 6. Root of 12 can be simplified to 2 root 3, so we have 6 plus minus 2 root 3 over 6. And then after factoring 2 out, we have 3 plus minus root 3 over 6, which can be cancelled to 3 plus minus root 3 over 3. So the roots are ugly, but that's okay. Let's take those exact values as they are. Since we have two roots, they will cut the number line in 3 sections. The lower root is 3 minus root 3 over 3, and the higher root is 3 plus root 3 over 3. Now we know that our parabola has a positive leading coefficient. That means our parabola really goes somehow like this. It's not relevant how narrow or wide it is. What's important is to see whether the parabola is positive or negative in each section of the domain. So since our parabola has arms up like this, the positive sections are outside of our roots, so here and there, and the negative section is in between. Okay, so reading this diagram, we can already give the final answer. Since our function should be smaller equal 0, we're talking about this section inside between these two roots, right? That's our solution. So the final answer is all x's from the 3 minus root 3 over 3 until 3 plus root 3 over 3. Should we include those endpoints or exclude them? Well, let's check. We have equation included inequality, so yes, we are including the endpoints because we allow the left-hand side to be 0. If this inequality would be strong with no equation, then we will draw round brackets here. Let's see the last example. This time we don't have 0 on one side, so what we need to do first is to bring everything to one side. So x over x plus 2 minus 2x should be bigger than 0. Okay, let's place everything under one denominator, x plus 2. So we have x minus 2x times the missing denominator, x plus 2, right? Larger than 0. Let's clean up the numerator, release the bracket. We have x minus 2x squared and then minus 4x. Everything over x plus 2 bigger than 0. Now, after collecting like terms, let's write it maybe over here, we get negative 2x squared, and then it's x minus 4x, so it's negative 3x. Everything over x plus 2, it's bigger than 0. Since we're supposed to factor every numerator and denominator, let's take negative x out of the bracket, and then we end up with 2x plus 3 inside. Everything over x plus 2 bigger than 0. And now it's time to create a table of signs. So let's list all the factors that we used. It was negative x, it was 2x plus 3, and it was x plus 2. Okay, let's draw our rows so we won't get confused. Those are all lines. And the final number line. And in the last row we'll record the result. So what are our critical numbers? It is 0 from the top one, right? This expression becomes 0 when x is 0. So let's say 0 is somewhere here. Okay. Now the second expression changes its sign when x is equal negative 3/2. If we can't see it, let's calculate this on the side. 2x plus 3 is bigger than 0 when 2x is bigger than negative 3, so when x is bigger than negative 3/2. Okay, let's say negative 3/2 is somewhere there. Negative 3/2, right? And finally, the last factor changes its sign at negative 2. Negative 2 is lower than negative 3/2, so let's position it somewhere there. It doesn't have to be perfect, but the numbers needs to be placed in increasing order the usual order on the number line. Okay, now let's record our signs. The first expression, negative x, changes its sign at 0. If x's are larger than 0, for example 2, negative x becomes smaller than 0. And if x's are smaller than 0, for example negative 1, the negative x becomes positive. So for all x's below 0 we'll have positive sign, right? Now 2x plus 3 is bigger than 0 when x is bigger than negative 3/2. So that's our critical number, and above it we have positive sign and below negative sign. Finally, x plus 2 changes its sign at negative 2. If x's are larger than negative 2, the expression is positive, and when they are smaller than negative 2, the expression becomes negative. The result, when we multiply or divide those factors, 2 negatives makes it positive, 1 negative is negative, 3 positive gives us positive, and 1 negative leaves us with negative answer. Let's go back to our inequality. We want to know when the left-hand side expression is bigger than 0. So bigger than 0 is here and there. Finally, we need to check the endpoints. What is the domain of our rational expression? Well, the domain of it is all real numbers except for the number that will make denominator 0, which is negative 2. So we have to exclude negative 2. Therefore, negative 2 can't be taken as a solution for sure. Now, since the inequality is strong, the other endpoints also can't be taken, because those x values, either negative 3/2 or 0, will make the numerator 0, and we don't have equal sign here, right? So those points will be excluded as well. Okay, that gives us the final answer. The solution is all x's from -infinity until negative 2, and then union with the segment from negative 3/2 till 0, no endpoints. Here we go. Well done.